Afternoon, everyone. So I think we'll make a start. We may have one or two just joining us in the next few minutes, but we can do this intro bit nevertheless. So, the place where we left off last week was that we were working through this PDF here. So, this simulation, evaluation, and optimization PDF. And we kind of done the simulation and evaluation sections of that. So we'd done the first two. We hadn't done them in that order. We'd done sort of the evaluation tools first. And then we progressed onto that I-beam, if you remember. So we sort of left the lesson kind of there. And then in the last sort of few minutes of that session, I quickly sort of talked everyone through what we'd be doing at the start of this session, which is this section here. So this is it mixes simulation and a lot of the simulation setup that we were doing last session on the I-beam, but it sort of adds on top of that, and it adds a kind of layer of automation where you can sort of semi-automate the task of changing your design to satisfy some kind of end goal. So in some cases, that's minimizing the mass of the part, or and you can also give it some sort of hard constraints, which is the stress in this part should not go above, and then give it a figure. But it allows you to put a certain amount of automation into that. So this is what we're going to try on this session. I will put one sort of proviso on this at the start, which is my system, when I was sort of demoing this yesterday, it was acting a little bit unstable. So if mine crashes again, I'll have to reboot SolidWorks and just drop back in, and obviously likewise with your systems as well. So in order to do all this, you're going to have the SEK version installed, or be using it through the virtual desktop, which is another option. And that means obviously you don't have to install SolidWorks at all. But it's up to you which one you use. They should both be largely the same. You should be able to follow along regardless of which one you're using. So, first things first, just let me get my screen organized. Have I got chat on? Yes, I have. And let me get my menu bar. Yep. So the first thing that we're going to do is we're going to model up this really simple beam component. And like the I-beam last time, this isn't a particularly exciting component. There are two reasons for that, really. One is that I want us to model this up, so I don't want something that's really long-winded, because this isn't kind of really a practice for creating models in SolidWorks. It's a practice for running simulations and design studies. So that's the first kind of reason for keeping it so simple. The second reason is we're going to be running calculations on this, and the more simple the model, the quicker those calculations are going to run. So it's kind of a twofold thing. But we're going to model this up. So I'm going to put that on my other screen, as I always do, and I'll keep referring back to it. But if you want to kind of model it up as I'm doing it, you can kind of get the dimensions and the shape of it from my screen rather than working from the PDF. So let's create a new file. This is just a single part file. It's not an assembly. What I will say as well, this won't take us the full session, hopefully. And at the second half of this session, we're going to kind of develop our simulation skills a bit further. And we're going to be looking at simulating entire assemblies. More specifically, we're going to be looking at simulating entire assemblies that are in motion. So we're going to be having a look at the kind of motion side of simulation. But let's get back to what we're doing. So I'm going to create an extrude. So I'll go features, extruded boss base, front plane is what I'm choosing to sketch on. And then I could use the rectangular tool, but because I know what we're going to be required to do later on when we want to modify this design, I'm actually going to use the line tool just to sketch out the approximate shape. So line tool, and I'm just going to kind of sketch approximately that. Just two lines. That's all I need at this point. And then I might... no, let's mirror them first. I was just wondering whether I was better putting a dimension on them first or whether we were going to mirror them first. But I think we'll mirror them. So I'm going to do a mirror entities, which we've used before on the sketch toolbar. Select those two lines because those are the two lines that I want to mirror. Then click on this mirror about box, and then I'm going to tell the system I want to mirror them about the vertical plane there, so that right plane as I'm looking at it. And then I can shortcut to OK that command just by right-clicking on the mouse. You can see there's a little green tick on top of a mouse icon there. So there you go, I've OK'd that mirror. Then just to show that it's possible, I'm going to do it the opposite way around. So I'm going to box select everything first before I even enter the mirror command a second time. So box select everything like that. Then mirror again, and you can see I've already collected all the lines that I want to mirror. So you can do it either way. You can initiate the tool first and then start clicking, or you can pre-select stuff and then it's already in there. So all we have to do this time is just tell it mirror about, and it's going to be that horizontal this time. And then I'm going to right click just to OK that mirror command as well. So that's our broad shape that we kind of need to represent this beam shape. So now I'll put some dimensions on it. So I'll go horizontal end to end is the first one. And that is going to be 200. And then I want a vertical on one end of 10. You can see because I've mirrored it, the other side kind of follows that as well. And then I want to do a vertical between these 2 points in the middle as well. So that point and that point there. And certainly initially, I'm going to set those also at 10, or I'm going to set that width in the center also as 10. So this is why I say, in this first instance, I could have quite easily used the rectangular sketch tool. I would have achieved exactly the same. But the beauty of doing it this way is that we get the ability to vary the sort of thickness of that center section independent of the thickness of the two ends. So that's what we're looking to do later on. And that's why we're setting the sketch up this way rather than using the slightly easier center rectangle tool that we could have used. And then, given that we're trying to put 3 holes through this thing, we could sketch the holes in, but that's kind of the messy way of doing it. What we should do at this point is just OK this extrude feature. So we'll get out of the sketch by saying we're finished in the sketch and clicking on the blue arrow at the top right. We'll give it a depth, which is a bit hard to see on the PDF, but I believe it's 5 mil in depth. And just because I sort of like to always put a plane down the center of these extrudes, just kind of a little bit of forethought, knowing that that's quite a useful thing to have. I think I'll switch it from a blind value to a mid-plane like that. So that plane that the sketch is on gets sandwiched in the middle of the part itself. And then I'll OK that. So that's the first feature. And then we've just got 2 features in this part. The second one being a hole wizard feature that's just got 3 identical holes in the one hole wizard feature. So we'll set this up really quickly. These aren't special holes. They're not threaded. They're not countersunk. They're not counterbored. They're essentially just drilled holes. So it's that icon there, just for a plain hole. The size I've already said. So if you want to set it to ISO standard, set it to drill sizes, because that by far gives you the widest selection of different diameters that you can choose from. And we'll set it to a 5 mil drill. So scroll down a little bit, 5 mil. And then I think we should be okay. So everything else wants switching off. You can see here that mine's defaulted to near side countersunk. I don't want that, so I'm going to untick it. And then in terms of the end condition, I think we'll just send these through all because we want them to pass through the part. So that's fine. So with all those settings sort of preset, we can finish with the type tab. We can go into the positions tab. And then I want to click on that side face there. So don't make the mistake of kind of clicking on the top plane by mistake. Make sure you've got the side face selected. When I click on it, my view should rotate round, so I'm looking normal to the plane. And then I'm just going to drop the first point on the origin there, so it kind of puts a coincident constraint, so it can't move, gets locked to the origin. And then I'll drop one over here and one over here. And then I don't want to drop the fourth one, so I'm going to hit the escape key. But I do want to put some smart dimensions on these. So I want to go back up to the sketch toolbar, select smart dimension, and then I'm going to dimension these left and right points relative to that right-hand plane, so that vertical plane in the center. And these are both 90 again. And again, I could have used the mirror command. I could have mirrored this point over there. So I only had to specify that one of them was 90 away. But just for adaptability in possible future redesigns of this part, I'm dimensioning them independent of each other. So I get that flexibility. I can move them about independently of each other. But I do lose that slight sort of time-saving element of just governing them both with a single dimension. So at that point, I can OK that feature, and we'll just inspect that that kind of has achieved what we thought it was going to. Has it passed all the way through? Yes, it has. And that's kind of the modeling portion of this exercise done. We're going to drop straight into simulating some stresses on this now. So, as I said last week, depending on which version of SolidWorks you're using, whether you've got it installed locally, whether you're using the virtual desktop version, you may have to go up to the tabs at the top here, click SolidWorks add-ins. Another thing is, some of you may not even have that tab visible. So you can see here, I can hide that tab. So if you can't see it there, if you go into the Tools menu and look down at the bottom, there's the same option there, add-ins. So either way, you get into it through the tab or you go into the actual menu version here. But essentially what we want is that option. SolidWorks simulation needs clicking on. And then you click OK from there, or if you do it from the tab, it's just a button that says, I think it says simulation on it or something like that. But you'll know when you've got it active because you'll get a tab that just says simulation on it, visible. So we'll click on that. Now, as I've already said, what we're going to do here, we're going to set up a simulation a little bit like the one that we did on the I-beam. Not identical, because I want us to use some of the other sort of options for setting these simulations up so that we get familiar with them. But we're going to set up a similar one as we did last week. Then we're going to run that, have a little look at the results. And then once we've created that original simulation at that point, we can use that as a starting point for our design study, which is the partial automation that SolidWorks offers you. So it partially automates redesigning your part based on the output of a simulation. But you kind of have to set up the simulation first. But as I say, we kind of covered setting up simulations last week, so we're a little bit familiar with that. It won't, someone's just said, it won't let them do the two separate widths. Let me just drop back into there then. So I'm going to edit the hole wizard feature here because someone's having a bit of trouble there. So I'll click on that. I'll go edit feature. And then it should drop me back into the menu that I came in on where I was setting up what type of hole I wanted. Somebody jumping in there? Oh, you've sorted it.
Yeah, sorry, I saw it.
Brilliant. Okay. That saves a bit of time anyway. We're always pushed for time on these sessions. That's the only thing. Yeah. They seem to go a bit quicker when we're sort of on site and we're doing them face to face. But yeah, we'll plow on. So we've got simulation switched on. We've got the tab visible. So we want to click on New Study. And then again, we're just using kind of almost the most basic study that you can set up in SolidWorks, the static here. We're not going to kind of dip into much into the other types, certainly not in this kind of module. So yeah, leave it on the default static, click on OK, and then again, we're just going to run down the icons here from the top to the bottom, addressing the ones that need addressing and kind of doing the setup in the ones that need that setup. And if you remember last time, the broad outline of what we did, we applied a material to the part. That was the first thing. So it was telling the system something about the sort of yield strength of the part or the Young's modulus. And we did that just by using one of the inbuilt materials, because we saw last week it's got a really wide sort of library of materials already stored in there. So unless you need something quite unique that's not in there, it's often good to use the ones that are provided. I'm not saying that it's not wise to check on the values sometimes. If you're making something that's highly sort of mission critical, it would be wise to use more than one source of the, let's say, the Young's modulus. So maybe go away and just verify that SolidWorks hasn't got it wrong. But anyway, for these examples, we're just going to pick from the library that's actually in there. So yeah, we set the material and then we fixed the part in some way. We added a fixture. We didn't kind of tackle connections because we only have one part. It's not connected to anything else as such because it's just a single part. Connections come into force a little bit more when you're dealing with assemblies. So yeah, we fixed it in place and then we applied some kind of load or force to it, and then we kind of calculated. There's a step in there which is meshing the part, but we kind of roll them into one and just mesh the part and then instantly run the calculation afterwards. So that's the broad outline of what we're going to do this time. So we need a material for this part, and I believe it is an aluminium and it is 1080 alloy. So the way that we do that is right click where it says part, apply a favorite material this time, because I've specifically picked one from this favorites list, so we don't have to kind of manually drop into the full library and search for the material that we want. So 1080 alloy, which is an aluminium. So that's been applied to the part. Again, it changes the appearance slightly there. It's worth noting, but it's not super critical one way or the other. If you really want your part, say, bright red, you can go back in and change it yourself. We kind of covered how to change the appearances of things the other week. We've already said we're not going to add any connections in here. So if we right click on fixtures. Now, if you remember last time, we kind of played around a bit with fixed geometry, rollers and sliders. I think that was it. Oh yeah, and we kind of dropped into advanced fixtures a bit as well. Well, this time we're going to use the fixed hinge. And so if I click on that, we're going to apply it to two cylindrical faces. We're going to apply it to this one here and this one here as well. So if you're trying to conceptualize what that sort of fixture is doing, that little animation to the left kind of gives you most of the data that you need in terms of that. So if I just put this constraint or this fixture on one of these faces, so let's say I deleted face 1 from that. If I put it on that face there, essentially how it will restrain this part is the part is free to rotate around that cylindrical face. So, but the position of the cylindrical face in terms of its Z position, so I'm pointing at the little Z direction here. So its position in Z and its position in Y and its position in X is not allowed to change. But the part that is kind of attached to that cylindrical face can rotate around the center axis of that cylindrical face, which is kind of what's being shown in that animation there. So the effect of me applying it to two cylindrical faces is that if you want to do the real world version of this, there's a pin passing through here, which is let's say a slightly slack fit. So the rest of the part can rotate around that pin. But then there's another pin passing through here, And then there's a high tensile steel cable going up from there onto some immovable, let's say, building or wall. So this is kind of, it's cantilevered out, it's supported there, and it's supported there. But these 2 points are, if they need to, free to rotate slightly around the center axis of these cylinders. So yeah, it has a certain degree of freedom, is the kind of point that I'm trying to get at. It's not being sort of too artificially kind of glued into position, which is what the fixed constraint does. That allows no rotation, no movement of any kind, which we kind of talked a little bit about last session, is somewhat unrealistic. If you're trying to simulate something as close to real world conditions as possible, the fixed constraint is a bit of a blunt tool. It loses some subtlety that you get in the actual real world setup. So yeah, fixed hinge on both of these. So we've set the fixtures up. We'll move down to loads. And again, we'll use a slightly different technique to last week. So we put a force through a particular face, I think, last week, which is a perfectly valid way of doing it. But that force could have been generated in several different ways. One of which could be that you are suspending a mass from it, and this whole experiment's occurring on Earth. So you know the gravitational field that's acting on that mass. You know the acceleration due to gravity. And the system gives you the flexibility to set your experiments up using masses and gravitational values as well. So we're going to do that this time. So distributed mass is what we're going to place. So it's that option there. We're going to distribute a mass on that face there. I'm just looking across onto the screenshot that we're working from to get the mass. It's 4 kilos. So it's quite a modest sort of mass that we're hanging off there. But without enacting gravity in these simulations, that mass, unless I started waving this beam around, and that mass obviously then has inertia, it has a resistance to want to kind of move initially and then change direction. And I'm not doing that, so I'm going to have to switch gravity on in this simulation. And the reason I'm making a point of that is don't assume that these kind of simulations that we're setting up, well, don't assume anything, I suppose, is what I'm trying to say. If you were to run this experiment in a lab, you wouldn't have to worry about gravity, as in you wouldn't have to switch it on. But these simulations don't occur in the real world. So you have to make sure that all the forces or gravitational constants are actually applied. So we're going to have to do that. So this is a second entry in the external loads setup icon here. We're going to have to right click again. Gravity is there. And all we have to do is give it a magnitude, which it defaults to Earth's gravity anyway. And then in general, it defaults to using the top plane as its plane of reference. And you get a nice big red arrow just indicating this is the direction that gravity's acting in. So that's all fine for us. But if we wanted to send it in a different direction, if this thing, we were viewing it kind of side on, but it was actually going to be used in that direction, you can see I can just change that from top plane to front plane to right plane. I think I can even click on the faces of the part itself. So yeah, you get the idea. Whichever flat surface I click on, that force acts normal to that surface. And if I want to reverse the direction, that's pretty easy as well. I can, just flip the direction. So we've switched gravity on. So all the loading kind of criteria has been set up. All the fixtures have been set up. We've defined what the material is. I think we're pretty much ready to run the thing. So if you want to right click on mesh, click on mesh and run. And then it shouldn't take it very long at all because it's a really simple model. So yeah, that should be more or less what you're looking at as well. So just so I don't miss any points that I've previously noted in this PDF. There was a step that we missed there. So there's a step there where I recommend that we kind of play with the coarseness of the mesh itself, which is probably quite a wise thing to do. So let's go back sort of half a step now and right click on mesh, and rather than clicking on mesh and run, just click on create mesh, because when we click on mesh and run, all the system does is it creates the mesh at the default element size, and then it just it runs a quick check that no errors have been generated when it did that. And if no errors have been generated, it just runs the calculation and we get the stress plot. But we can go in and kind of have some input into how that mesh is set up. So that's what we're doing now. So I just clicked on mesh rather than mesh and run. It then gives me a warning saying if you remesh it, all these results will be invalid. That's fine. It's just going to delete them. We're going to run it again in a minute. And then I get to this screen, which we haven't really seen before. So let me click on the green tick here, just so that I've got something to point at. So that is essentially what the meshing step is doing. And this is the kind of finite element bit of finite element analysis. It chops that solid shape that we had before into a finite number of elements. And that's what these are. They're little sort of triangular-sided 3D shapes. And what the system does is at these node points where the triangles meet each other, it runs the force and stress calculations that it needs to run. And then when it gives us our readout at the end, so let me just quickly run one so I can point at this as well. This, even though it looks nice and smooth, it's not. It's a... if I can switch the option for smoothing off on this. Yes, it's in here somewhere. Color up. There we go. Continuous. Discrete. No, that's point. Line. No. But essentially, that's nearer to the actual output of the calculations. It just smooths them for our sort of benefit visually, just to interpret them. But essentially what it's doing is the mesh, it's calculating these stress figures at each point where the triangles meet each other. And that's kind of the only way it can do it. It can't do it as one continuous shape. It must chop it up into discrete little triangular sided elements in order to run its calculations to generate these stress plots. So with all that being said, what we can have an influence over, if we create the mesh first, is if, let's say, there's an area, a particular area on the part that we feel that we'd like a bit more data, or we'd like it meshed a little bit more finely, we can go into create mesh and we can whack that all the way up to fine, create a new mesh, and you can see, well, it's not that obvious there, but those element sizes are significantly smaller than that original default size mesh. So that's the broad outline. There's a whole kind of lessons worth there in terms of tweaking mesh sizes and element shapes. And again, I've given you the really sort of brief overview there, which is just slide this slider from left to right. That's as much as we're going to go into that at this point. But just know that what you can do is affect the mesh size as it comes into contact with certain design features in your design. So say I was really interested in this area around this central hole, I could have a mix of the two mesh sizes. So I'm bringing in, this was the finest that it allowed us to mesh it at on the right-hand side here. And this is the coarsest that it allows us to mesh it at the left-hand side. And with some of the more advanced mesh controls that you can put in here, you can have certain, let's say, holes through your part really finely meshed. And then gradually, as you get further and further and further away from the hole, the elements get bigger and bigger and bigger, because you're less worried, let's say, about a portion of your part down here that you know the stress levels are really low in. So it would be pointless just meshing the whole part in a really fine mesh. And the reason that it would be pointless that I haven't kind of stated yet is just the calculations on the right-hand side mesh here will take significantly longer than the calculations on the mesh on the left there. So that's the trade-off. Calculation time is what you're trying to maximize. And obviously the reason for that is just if it does calculations at every little node point where triangles meet, there's a lot more of them on the right there. So it's doing the same calculations, it's just doing a greater quantity of them to give us a more detailed rainbow plot when we actually come to the stress plot there. So yeah, that's kind of the brief sort of look into meshing things. As I say, it's a far more complicated sort of area than that, but that's kind of, it gets you up and running. It gets you sort of appreciating it at least. So in the PDF, what I have actually written is that it's probably worth us turning the default mesh quality down slightly. Even though we're generating this initial stress plot quite quickly, when we actually set up the design study later on, it takes a lot longer to calculate. So if we can make the mesh slightly coarser here, it will speed up that calculation time later on. So yeah, somewhere in that order of kind of magnitudes, somewhere there. So I would say just to the right of the word coarse is probably reasonable. But again, you don't have to get too hung up on that for this particular example. So I'm going to set mine about there. That's fine. And then click on OK. So you can do this process. You can mesh and then you can run if you need to have a bit more control on the mesh itself. And the way that you do that is once you've meshed the part and you're looking at the mesh plot there, which is what we're doing, if you right click on the top icon that says static one, there's a run option in there. Or there's also an icon that sits on the top toolbar. So either one will do the same thing. It will just run the calculation to give us our stress plots and our deformation plots. So that is where we should be at this point. And how are we going to interpret that? Well, the first thing that's jumping out at me is that the yield strength of my material has been exceeded in certain parts of the plot there. So there's certain parts of the plot that if this simulation is to be believed, will permanently deform. So that's never good. So we built this out of aluminium, and even when we release the load there, it will still remain in a slightly deformed, slightly kind of sagged state, which is not a good thing. And if you do that over and over and over again, obviously it's going to fatigue pretty quickly. And that spot there is going to kind of work harden, and then it's arguably going to split after it's work hardened, and then it's going to be sort of a cascade effect, and eventually it's going to snap through either below, well, probably above this hole. So yeah, that's never good. But we kind of talked about the fact that not only in real sort of design activities do you try and design all areas of your part to be within the yield point, so lower than the yield point, you tend to actually give them this factor of safety, this FOS. So you wouldn't even be just under the yield point. You'd probably be at a quarter of the yield point, or maybe even an eighth or a tenth of the yield point if you're building skyscrapers, let's say. So yeah, this is pretty bad, basically. We've got to address this in some way. So what are we going to do next? How are we going to address it? Essentially, we're just going to add more material in the center section. It seems like sort of the simplest fix that we could do. And given the way that we set our model up, we can just drop back in and bump that center section up to double its previous width. So you can see there, it's reading at 20 when we get back in. So this is kind of the manual way of using simulation. It's run your initial experiment or your initial simulation, look at the results, and then make a change to the design based on the results. Now, these results show that we've overstressed the part. It needs some sort of reinforcement. But likewise, if you were well under the yield point by a factor of 100 in all areas, you could start removing material from your part if the mass of the part was a sort of a favourable thing to reduce. And as I say, depending on what sort of project you're working on, that is often quite favourable to reduce the mass. But if it increases things like machining time to manufacture the part, then maybe not. It depends how critical the mass is in its final function. So yeah, let's add a bit more material in the middle. So the way that we do this, currently we're in simulation mode. So you can see we've got this static one selected at the bottom. That's our static study that we have set up. You can see that we're in the simulation tab at the top. In order to get back into part modeling mode, we have to click on that first tab at the bottom that says model. And then the plot will temporarily disappear and we go back as we were when we were modeling this part up in the first place. So that's what you've got to do. If you want to make changes to it, you've got to kind of drop back into part modeling mode. And then because I've got Instant 3D selected on my features toolbar there, so you can see that option switched on, I should just be able to click on the extrude there. All the governing dimensions that are governing the shape of that extrude become visible. And I should just be able to click and drag on one of these blue spheres like that. Obviously, you could drop back into the sketch and edit the definition of the sketch and do it that way as well. Either way, it's just this is probably the quickest way of doing it. So we've done that. Let's drop back into the simulation and rerun the simulation. So I'm going to click on that tab that says static one, because that's our static simulation. Now, these little yellow kind of, they're not exclamation marks, but they're kind of down arrows and they're highlighted in yellow. It's showing me issues with this simulation. And the main one here is that the mesh that we previously made is now out of date. So we're going to have to remesh the part. So hopefully, if I just right click and go mesh and run, it will use the existing mesh size, so those element sizes that we set to be a little bit coarser than default. It will keep that element size, but it will remesh with the new shape, the new design that we've just kind of modified to. So we should just be able to go mesh and run, and all those warnings should disappear. Yeah, they've all gone. So that's essentially what it was trying to draw our attention to. The previous mesh was still in memory, where the part had a flat top and bottom, so it was 10 mil all the way through, and we just had to remesh it, and then it was happy again. So yeah, what have we done? Have we cured the problem that we had initially? Yes, it appears as if we have, because essentially our yield strength is 2.7 times 10 to the 7, so it's 2.7. Our plot maxes out at just over 1, and that's also times 10 to the 7. So you can sort of disregard that bit if you're just comparing these two. So yeah, 2.7 or going on 2.8 is where the material starts to permanently deform. The max in our new design is not there yet. So yeah, largely it's a reasonable design. We haven't tackled how much of a factor of safety it's got, because I would argue it's actually still running a little bit close for my liking, even though it's down below half. But yeah, certainly for this exercise, we're going to work to the yield point rather than working to a factor of safety, just because it simplifies the exercise slightly. So the next bit of this is, what have we done? We've done that section there. We've done this section here. This sort of innocuous looking couple of sentences. Now alter the dimensions to minimize the mass. Set up a design study to automatically find the best solution. So that's kind of the bit that we're on now. So it's setting up a design study. And again, you can resolve this into a few kind of simple steps. The first step is saying to the system, these are the values that I'm going to allow you access to explore different designs. And the ones that we're going to allow it access to are the end thickness, which currently is 10 mil still, and the middle thickness, which is currently 20 mil. And again, the more of these values that you allow the system to have access to change in your design, the slower this process is going to be. So just in the same way that setting the mesh up, the more finite elements you give it to calculate, the slower it's going to run. The same applies here. Because if you can imagine a table where it's got all of these potential sort of dimensions in the table, and it has to explore every variation of every dimension coupled with every variation of every other dimension. So that very quickly sort of mounts up. It's the amount of steps that you give it to vary in every dimension times the amount of steps in every other dimension. So that's why I've limited it to just 2 that we're going to allow it to change. The center thickness and the end thickness, and nothing else. So once we've set that bit up, then we give it kind of a hard constraint or a hard rule that it cannot break. And in this case, we're basically going to say the highest stress value that should be encountered in the simulation should never go above that value there. So be less than that value there. And then the last kind of piece of it is that you give it an overall goal that it's tending towards. So this isn't kind of a yes-no question or a hard limit or constraint. It's just overall, we're looking for the design. If there are multiple designs that satisfy this constraint, then pick the one which is the lightest. So minimize the mass. And once we've set these 3 kind of broad areas up, then we set the system running. And what it does in the background is it modifies our design. So you can see, hopefully, just on that screenshot there, there's a design that has a really thin kind of end to it. So it actually modifies the design. It runs however many scenarios result from the range of minimum and maximum that we allow it to change those dimensions within. So in this case, it's going to be 20 simulations. It goes away, runs 20 simulations on 20 different designs, and then it picks the one that not only passed the constraint, but that was the lightest, so had the minimum mass. And it highlights it, and it modifies the part in your part window there to be those values, essentially. So let's start setting that up now. So let's see if I can remember how to jump straight into design studies. Don't do this step. Just let me do this step. Yeah, that did work, I believe. So let's do it that way. So in your static tab, which you should still be in, if you right-click on the tab and then create new design study, it should be at the bottom there. Like that. And then this window should be kind of familiar because it's the one that I was just kind of pointing at in the PDF. Where is it? That one there. And we're just going to work down it from the top to the bottom. So the first one is the dimensions that we're going to allow it to change in the design. So click here to add variables, add parameter, and then all the dimensions of the part should become visible. And we're going to just click on one of them. So we'll click on that 10. It collects the value into there, so it's collected the 10. We have to then name it. So we're going to call it end thickness, like that. Press enter, and then you'll be given the next row in the table. So then click on that next row down so that row's selected, and then collect our next value. So you can see mine's sort of hidden in the middle of the part. That's because the sketch is sandwiched in the middle of the part. But if I hover over it, it appears. So it is there. So click on that value. It collects it into the value cell, And then again, I just need to name it in the first cell. So mid thickness, press enter. So it's got those two. And then I don't want to enter another one. So I can just click on OK at the bottom. And then what we have to do is we have to tell the system, I'm going to allow you to modify this value. So end thickness is the first one that we're going to tackle. I'm going to allow you to edit it anywhere between a minimum value of, so currently that's set as 5, and a maximum value of, currently it's set as 15. And then within those that range of values, I want you to jump in steps of, and in this case it's set as 5 mil. So I think what we'll do, we'll just tweak that slightly, because I wasn't seeing any stress problems around the hole on the end of the part. So I wouldn't really like it to go up above its current value of 10. So I think I'll set the max as 10. Because again, what we're looking to do is we're looking to target our investigation to a sensible range. Because if not, and we just widen the range right out and put the step size maybe down to something ridiculous like 0.1 of a mil, then it will take maybe a full day to do the calculations. So you've got to be a little bit sort of targeted in the range that you're looking at and the step size. I think we'll allow a step size of 2. So obviously I've kind of hashed all this out before we did this session. You'd have to kind of maybe do a sort of dry run on this, maybe with, I don't know, 30 scenarios, and then see how quick it was calculating, and then maybe cancel that one and come back in and maybe make your step size a bit bigger if you wanted to speed it up. You've got to kind of be willing to play around with it a little bit. So we've set up the range for the end thickness, essentially. Now we need to add the mid thickness into this variables that the system is allowed to change. So there's a drop-down menu there with any variables that you've already set up. So we set up mid thickness, so it's just there to click. And then again, I'll give you the values that I kind of... So the minimum, we already saw when we ran the first simulation that 10 mil in the center here is too narrow. So I would say the minimum doesn't want to be any less than 11. Probably 11 is still a little bit low, but we'll set the minimum value as 11. We've seen that 20 has kind of overshot what we're looking for. So 20 is a bit too much material. So I think we'll set this one at 19. And then again, step size 2 seems reasonable. And as I'm changing these values, that total active scenarios changes as well. So I've just temporarily changed the step size down to a finer step size here to 1. And then you can see the total active scenarios, or the total simulations that the system's going to have to run when we press run, has gone up. So you can see it in real time. So if you remember how long the original static study took to calculate, you could kind of do the calculation yourself as to how long this design study is going to take to calculate. Because it's going to run 20 versions of the static study. So if that took, say, I don't know, if that took a minute, this would take 20 minutes. So you get the idea. So we've set the variables that we're going to allow the system to play with. Now we're going to set a constraint of some kind. So we want to add a sensor because we want to monitor a value, some sort of value. You can remember we added a measurement sensor in one of the previous tutorials that we did, when we were measuring how far that center of gravity was outside the base of that kind of component. We did this similar thing. So we want to add a sensor. Then it will take us into this sensor setup menu. The thing that we want to monitor is a stress level in the part. So this is the kind of hard rule that the system cannot break. We want to say the stress in the whole part can never get above, and then give it a value that it can never go above. So it's not a mass property. It is some kind of simulation data. So it's some data that gets generated by the actual simulation itself. Simulation data, stress, yep. We don't want it in PSI. I think it was in Newton meters squared. Let me just check. Yes, it was. So yeah, newtons per meter squared. The max in the entire model. That's kind of what we're looking for. So click on the green tick there. It gets entered into that row in the table, and then we have to set up the kind of criteria that we want to apply to that. So we don't want it greater than a value, we want it less than a certain value. So is less than. You can also have is between if you're looking for certain values. Maybe a measurement value you might be interested in. In between is quite useful for that. But yeah, in this case, or greater than is good when you're looking at factors of safety. So obviously, if I wanted a really overbuilt part that was 10 times overbuilt, I could say is greater than, and I could be monitoring factor of safety, and I could say is greater than 10. But yeah, you get the idea. In this one, it's stress is less than, and then I think I remember it was 2.7 times 10 to the power of 7, I think. I'll just check that. So yeah, that's the syntax of how you type that anyway. 2.7, then asterisk 10, and then that little thing when you hold shift down and press the 6 on the keyboard, you get that little up arrow looking thing. That should give you the right value. I'm just checking on that now. Yeah, it was times 10 to the 7. So when you've entered all that, if you just quickly click off that cell and then back onto it, it will change the notation to include the little E and the plus. So you'll know that you've set it right if you're looking at that. 2.7 E plus 0.7. So we don't want the stress to ever get any higher than that in any part of the design. So there's only one last thing to do. Click here to add goals. So the overall goal is that we want to minimize the mass of the part. And again, we're going to have to add a sensor in. And again, we could have set these sensors up when we were modeling the part itself. We saw that it's possible to do that, again, on that balance part that we were kind of working on at the start of last week. So you can add sensors in either on the fly as you're doing these design studies, which is what we're doing now, or if you've already created some sensors in the part, they will be listed here as well. So either way is okay. So add a sensor. This is a mass properties because it's just the mass. It's not simulation data, obviously. And then again, just to have a quick sort of browse into what sort of things we could select here. Volume is considered a mass property as well, surface area, center of gravity in X, Y, and Z, those sorts of things. But in this case, it's just the plain mass that we're interested in. So click on the green tick. It accepts that into the table. What are we trying to do? We're trying to minimize it. And then again, there's various options in there. Minimize, maximize is exactly, depends what sort of quantity your sensor is monitoring. But yeah, minimize mass is our overall goal. So at that point, we should be able to click run. And then cross your fingers that my machine doesn't crash. So yours might come back in and finish before mine. I'm not sure what sort of hardware. It will probably, if you've got the sound on as well, it'll be bonging in the background normally. I think the sound signifies that these two setups, or these three setups, have failed. So what we're looking at, we've got a table that's been pre-populated with all the different variations that it's going to try. So you can see there's N thickness on the top row here, and it's got 7, 9, 10, 5, 7, 9, 10. So you can see it vary in the N thicknesses. We've got mid thickness on the one down here. The fact that these have been coloured in red, these three rows, means that those designs have actually failed in some way. So you can see, again, if you look at the table, we want a stress value under 2.7 times 10 to the 7. This stress value is 3.7 times 10 to the 7. So that's why it failed. It can actually also fail. Say we gave it a thickness for this end face here that was so thin that it interfered with the hole itself. that would be a failure as well, because obviously you can't put a 5 mil hole through a beam which is less than 5 mil. So potential failures can include a failure of the model itself to rebuild, or it can include a failure as in the constraint that you've set also can fail. So yeah, mine's come back reasonably quickly there. So what it's done is, first thing, it's changed the actual model to the optimal. So this optimal scenario, which is actually row 5 on my table, you can see it's been labeled as scenario number 5. Whichever one wins, or whichever one is the optimal design, it brings it way over to the left-hand side here, and it colors it in green. And it applies it to the part itself. So you can see, if I now click on the initial column in the table, it will change my design back to the initial. So it's a subtle change. Oh no, it didn't change to the optimal, sorry. So I'm clicking backwards and forwards between the initial design and the optimal design. So you can see what it's done there. Now the next step here is to accept the optimal, but then use our sort of nous as engineers and say, that is a bit too thin. That is a failure of our setup of our simulation, that we've somehow supported this section a little bit too perfectly, and we've not set up our design study quite to be as thorough as it should have been, and we've ended up with a quite concerningly thin wall there. So I would then go in and correct that manually and rerun my simulation. However, this center section, I'm reasonably happy that a 30 mil thick center section would be perfectly fine. So the last kind of bit of that is to, here we go, accept the optimal, accept the changes that it's made, but then rerun the static simulation to investigate the thin walls around the end holes in a finer mesh size. So this comes back to us kind of playing around with the element size a little bit. Manually adjust the design as needed. Now this is kind of, it's meant to illustrate that you don't solely rely on the design study to design your part for you. It's just another tool in your toolbox of parts, of features in SolidWorks to use. Sometimes you use a manually controlled simulation and you'll manually make an adjustment, and then you'll go back into the simulation and run it again, and then manually go back and make an adjustment. Other times it's more useful to run a design study and look at multiple variations of your part. Yeah, and you have to use both kind of side by side. Sometimes you use the design study. Sometimes you take what you've learned from the design study and then you kind of augment it yourself using your own simulations or other criteria. If you've researched some criteria about thicknesses round bearing surfaces, say, you can put that into the design as well. And then the final bit, now update the overall design with the goal being to further lighten the part and then rerun the design study to use through holes and or cutouts to remove more material where possible. So I think certainly that final step there, I'm going to leave that up to people to do kind of in their own time. But what that is aiming towards is the fact that if I accept the optimal now, and then drop back into my static design study and just do a mesh and run. So this is the optimized setup. I can sort of see that there's potential here to thin out this center bit slightly. This is relatively speaking under quite low levels of stress. So if I was to remove any material from this part, I could potentially do something such as this sort of setup. So let's say I sketch on that surface there and then maybe take out a little chunk somewhere there. and then do an extruded cut, but maybe not all the way through, maybe just 3mm into the surface. 3mm maybe a bit too much. 1.5. So I could start doing these sorts of things where I'm trying to lighten the design, but I'm taking material away from the lowest stressed areas of the design. So just so it wasn't lopsided, I'd probably mirror that. So it was duplicated over on the other side, and obviously over to this side of the part as well, like that. And then rerun the static again, and maybe see how that's affecting things. And again, this is meant to kind of simulate how you would use these simulation tools whilst you were designing. The idea is, don't do a design and spend too much time. Get into the simulation side of things quite early on, because it's quite a useful tool to kind of guide you whilst you're actually still in the stage where your design's quite kind of fluid and it hasn't been locked down too much. So yeah, that was the kind of last section of that PDF. That was kind of what it was kind of hinting at. Add some more kind of features into your design tree, if you like, to actually remove materials where it's not wanted, and then maybe set up another design study here. I mean, I've just taken out some very simple slot-shaped cuts, but arguably what it might be wiser to do is kind of mirror that angle. So that angle of the top edge, you could create a slot that's slightly wider at this side than it is at this side. So it's sort of parallel with those angles. You see that in a lot of, certainly suspension parts. If you get inboard shocks, I forget the name for it, where the shocks are kept inboard on the car, and it's got sort of a push rod setup. You get a lot of machined aluminium components like this, but they transmit the force around a right angle, and they have a lot of these kind of machine pockets on them that kind of lighten them so that they react quicker and they weigh less overall, so they're weighing the car down less. So yeah, it's worth just having a play around with that. But certainly you use the design study and just the manual static study kind of in backwards and forwards. You kind of run a design study, see what it came out with, apply that to your design, and then maybe make a few more changes, run a new static simulation or rerun the same one, see how it's affected it, maybe set up a slightly different design study where the system can vary some other values in your part. Yeah, and use them as early as possible in the actual design process. So, are we okay to kind of move on to the assembly that I got sort of slated to do in the second half? Does anyone want me to kind of go through the bits of that? Or shall we go on? All good. I'll take that as for everyone. Okay. Again, there are kind of videos linked in the learning materials that have got a lot of this kind of content in there. So if you want to dip into any bits of this, yeah, tutorial videos, you can do that. And you can always bring up questions back to one of the later sessions as well. So what are we going to do next? You need to download that zip there. So the one that says motion and stress.zip. You need to download that, get it unzipped into a folder, and that's where we're going to be working from. And the PDF to go with it is that top one there, motion analysis with stress. So if you want the PDF open, you can get that open as well. So that's what it looks like at the top of the PDF. So I think I'll shut this one down. If you want to save that we were just working on, it might be useful. You can go back in and sort of pick it apart then and see how we set things up, maybe. So here's where I've kind of unzipped mine to. So it should unzip to a folder called motion and stress. There should be various files in there. Now the PDF is worded as if we have loaded the assembly up that's located in there. So there should be those files located in it. There should be a file called assembly that's all the parts assembled together, and then there should be 4 part files. Now if you've just seen the part files, it's probably that you've got the filters switched on down here. So I can filter what I'm looking at to just view the parts if I want to, or just the assemblies, or just drawings if I had some drawings in a folder, or you can just set it to all files there. So as I say, it's worded as if we're going to load the assembly up. Now I tried that earlier and I was having lots of trouble, and then I thought, just as an experiment, I'll rebuild the assembly myself quickly, and then it worked fine. So I think we'll do the same thing. So don't load the assembly in. There may be something slightly sort of wrong with that. So what I'm going to do, I'm going to select all the part files like that. So I just press shift. I clicked on the bottom part file, which is wheel, the way that I've got them sorted. Held down shift, clicked on the top one, and it did kind of a bulk select on all of them. And then if I click on open, it will one by one open those parts up in SolidWorks. So there's the first one, and it will just run through them one by one. And there's the final one. So I've got them all open. Oh, there's the final one. And then normally it kind of arranges them into this kind of cascaded sort of window setup there. So I've got all the parts open. The reason I've done that is that's arguably the easiest way to kind of build a simple assembly like this. If you've got all the parts open in the background already, they're kind of readily available in the assembly environment. You can just drop them in one by one. So that's why I've done it that way. If it was a huge assembly that I was going to make that had hundreds of parts in, I wouldn't do that because it would slow the machine down way too much. But it's acceptable for this. So what I'm going to do now, I'm going to go new file, just like we've done before when we're creating part files. So new file, assembly is what I want to create. So I'll double click on assembly. Give it a sec to do its thing. And then I should get an empty assembly. There's my empty assembly. There's all the files listed in open documents, which otherwise I would have to kind of browse onto the hard disk and find them one by one. So the first thing that I'm going to put in is base. And this is a good sort of point to practice what not to do. So what not to do is just, when you've selected the file that you want to put down first, just click in the window. That is bad. That is very bad. And the reason for that is, look what's happened. It's just fixed it in a position which has no relation to the assembly planes at all. So there's the 3 assembly planes. There's the origin. And just wherever my mouse pointer happened to be is where it's fixed this thing. So that's really bad. And it is fixed. Again, the first item that you place in an assembly, SolidWorks applies something known as the fix command to it, which is not technically an assembly mate as such. It literally just fixes it in space wherever it happens to be. So let's back up a minute. Let's delete that. And then we'll go into assembly again. So insert components. This was the kind of menu where I was. Click on the thing that you want to insert, base, and then just click on the green tick there. And you can see what happens. When I go near the green tick, it jumps so that the part is now located with the part origin on top of the assembly origin. So the part origin that's stored within that part and the assembly origin are coincident with each other. That's far more preferable. So you just click the green tick, but it's hard to resist the urge to just click in the graphics window. But yeah, click the green tick, and then it locks it into that position, which is far more sensible. Then we'll put the rest of the components in. So I'm in the assembly tab. I'm just clicking insert components. Let's put the bearing block in. Now I know which way around this is supposed to be oriented, so I'm gonna use these little rotate on X, Y, and Z commands to get it in position. So I'll click the X, click it again, click it again. Yeah, that's better. It's just useful to get it in the right sort of orientation relative to the mates that you're going to apply to it in a second. So let's apply those mates. Let's put one between the underside of the block and the kind of bottom of this slot there. So I was holding down Control as I clicked on those two faces, and I want to make them coincident with each other. So again, a lot of the terminology in assembly mates, like coincident, parallel, it mirrors a lot of the stuff that's used when we're talking about relations in sketches. So make it coincident. Then we'll have a little play around with what we've done. Yeah, so it stays coincident with that bottom of that slot, but it's free to kind of wander around in Z and X. So we're going to stop it from doing that now. So I want to click on that side face and hold down Control, click on that side face of the slot, make those two coincident. So again, if we want to investigate how it's still free to move, it can slide around in the slot. That's fine. So what we could do is a final step. And again, had we loaded in the pre-made assembly, this is what we'd have discovered is, well, let's do it rather than talking about it. So what we can do is we can set a special type of assembly mate that will allow this, what's it called, bearing block to move between a certain position and then a certain position over here. So let's set that up now. So I'm going to click on the end face of the bearing block, hold down Control, click on the end face of the slot, and then I'm going to select that option there. Limit distance. So if you hover over it, it should say limit distance on it. Like that. And what we're looking at here is the current position between those two faces that I've clicked on. So they're currently around 76 millimeters away from each other in my model. Obviously yours will be whatever yours is. And then the boxes below allow us to set what we're going to allow that distance to get to as a maximum. So let's set it at, say, 100. And what we're going to allow it to get to as a minimum. So let's set that one at 0. And then press enter. And then I think we'll have to click on the green tick as well. Yeah. Then we can investigate what we've just done. So that's what we've just done. That slider, or bearing block as it's called in here, can now only move between those two limits that we've set for it. Now, in actual fact, when we come to run the motion simulation on this, we're going to turn that mate off. But it's worth knowing that it's there. Sometimes you're going to want to use that in your assemblies that you're creating. It's just, as I say, for this particular example, we'll actually suppress it. But we'll leave it on for the time being. And we'll delete it in a little while. So insert another component. Let's put the wheel in next. And I'll just click there. So now I'm using that ability to just click in free space and drop a component. So I did it with the wheel there. Wherever my pointer happened to be, I just clicked and it got dropped into the assembly environment. And the reason I'm happy to do that, after I've placed the first component or the first part in an assembly, all the subsequent components, when I place them, they come in totally underdefined. So their position is entirely free to move in any direction, like this, and rotate in any direction. It's only that first part that you place that gets locked into position. So that's why it's kind of key that first part that you place, you click on the green tick. But all the rest of them, you can just kind of drop them in the environment initially and then go about adding assembly mates to them after you've done that. So let's put a concentric mate on that hole that runs through the center of the disc and that kind of peg or upstand there. So concentric is what you want to make those two. And then again, you can have a little play around with this, see how it's free to move. Yeah, so it appears as if it's still free to spin and move up and down. That's okay for the time being, but we'll get rid of that in a second. So we'll put another component in, the last one. So this is going to be the link. And again, its orientation is kind of out a little bit. So I'm going to use this kind of pre-positioning, I don't know what you'd call it, toolbar to actually flip the direction a little bit. So what do I want to flip it on? I want to flip it on X. Why is it not working? Have I just clicked off and ruined it now? I think I probably have. Oh, how annoying. Yep, still not working. I'll just place it then. I'll place it there. And we'll put some mates on it instead. Just as an aside, if you want to kind of reposition something slightly before you add the mates to it, an easy way of doing that is to right-click on the item in the assembly and then click on that icon there. Move with triad. And you get this kind of useful little triad tool that allows you to lock its movement or rotation to a single axis if that's useful. So I find it quite helpful sometimes to move things into their approximate final position, because you tend to have less instances where you add a mate to something and the mate's in the wrong direction or upside down or back to front. If you can get them into the rough approximate final position and then add the mate in, things tend to go a lot more smoothly. So let's add some more concentric mates onto the end of the link and the corresponding components. And then I think what I'll do, just let me look at this thing side on. Yeah. So I think I'll put one, the underside of that link. I know it's not very realistic, but I think, well, let's make it a distance away from that face. Let's make it 2 mil away from that face there. So I clicked on distance there. I obviously clicked on the two flat faces, clicked on distance, entered 2 mil, pressed enter, and they moved into position. Then I think I'll add a cylindrical mate between that face there and that one there, like that. So we're getting there. And then I think I'll do the underside of the wheel. And is this going to work? Yeah, I think it should. Underside of the wheel, top of the base. And again, I'll probably put a little offset between those two, maybe 2 mil again. And then a quick inspection just to see what's happening. Yeah, that looks okay from the side. So this is a moderately unrealistic kind of assembly. You would need some method of kind of holding this link up against gravity. But given that I've already said, unless you switch gravity on in these simulations, it doesn't exist. So I'm assuming that this disk thing would drop under its own mass down onto that top surface there. But I am making a sort of assumption there that we're operating on Earth under Earth's gravity. We may be floating around somewhere in the spacecraft. So yeah, and this is only a tutorial, but it's worth considering these things just so that you're aware of the limitations of what you're simulating or your simulation. So that should be set up. And then we're going to run into some problems with our limit. You can see our limit's coming into effect there. So I'm going to delete that limit. That was just kind of a illustrative, just this is how you put limits into an assembly. So you can see I'm just clicking and dragging on that just to check out how it's free to move. So if you want to delete a mate, you can find it inside the relevant component. So it's this component that the mate's stored inside, and also this component. Oh no, it's not. It's just the bearing block, sorry. So if you browse inside the bearing block there, there's a mates folder, mates in assembly one. And then if you browse in there and just kind of hover over these, they will highlight in the actual graphics window. So it's that one there, limit distance. And you can just click on it and press the delete key, and you get a little confirmation, and then hit yes, and it's gone. And then I'll investigate that we're as we should be now. Yeah. So it's free to do a full rotation. So that's sort of the easy bit. Setting up the assembly is just kind of a bit more practice for us building assemblies. It's not really part of the simulation step. So there is a step here before we drop into motion simulation that you're going to want to do. It's wise to set the bearing block there to sort of halfway through its travel. It seems to present less problems. When we get into motion, what we're going to do is we're going to spin the rotational speed of this component, this wheel, up from 0 at rest to reasonably quick over a period of time. And the sort of calculation side of the motion section in SolidWorks kind of has more problems when the bearing block is at one end of its limit of travel there. So if we start it there, sometimes it throws a little bit of a spanner in the works. I could investigate why that is, but take my word for it. Put it sort of halfway along, and it will present less problems to us. So we're ready to drop into motion now. We have our assembly set up. It's probably wise to save this assembly before we do that. So I'm going to click on that icon there to save it. I'll then get prompted to give it a name. So it's saying, do you want to rebuild? Yeah, we're happy with that. Rebuild. And then I'll call it whatever I want to call it. So motion. Oh, that's on my other screen. So I'm just typing motion and pressed enter. So it's saved that now as motion solid assembly. You can see there. So just like when we're running a static simulation, like we've done before, the motion plugin or motion add-in for SolidWorks isn't necessarily switched on all the time. So again, on the virtual desktop, I believe it is switched on all the time. But if it's not, if you haven't got a tab showing motion at the top, you should be able to go into SolidWorks add-ins and click on motion. Having said that, I don't think you get a tab, but we'll see in a second when mine switches on. So yeah, mine's on now. So no, you don't get a tab. But you'll know when it's switched on because that will be kind of, I want to say highlighted, but it's sort of low lighted. It's got a dark grey colour to it. That's SolidWorks motion icon. And then all we do is go down to the bottom of the screen where sometimes we see that static study. And if you click on motion study 1, we've essentially started a motion study now. We're ready to set one up. So let's, just before we do that, I think we'll double back and we'll look at this kind of flow chart that I've put in at the start, because that will make more sense once we've completed this. That's probably worth just soaking in, and again, that'll make more sense once we've kind of done this simulation as well. So in a sense, we've covered that already. Static part simulation. We covered it with the I-beam. That was just a part. It was a part in isolation, and it was static, and we ran a simulation on it. What we're doing now is arguably number 3, and then next week we're going to have a look at a combination of number 3 and number 2 as well. And arguably number 1 comes into sort of effect again. So yeah, keep that in mind, but we'll come back to that and we'll talk about that flowchart a little bit as well. But ultimately, what we're looking to achieve as we do this is to run our little machine. So our little machine that's got this spinning plate. The spinning plate, we impart some motion into the plate. So we imagine that in SolidWorks terms, it adds a motor to the plate, so the motor can accelerate and decelerate and keep spinning at whatever speed we specify. And then that plate obviously will drag that link around its perimeter. And as it drags the link, it will cause that bearing block to slide backwards and forwards. And as all that is happening, the link will undergo sort of compressive and tension forces as the bearing block initially doesn't want to move because we're kind of disregarding friction. I mean, it's in this simulation, but it's not the main force. It's just the fact that the bearing block has mass means it's resistant to moving initially. And then once it gets accelerated up and it starts traveling along here, it then has to be decelerated, and then it has to accelerate in the opposite direction. So the link sees compression and tension and compression and tension. And we can plot the stresses that it sees. So we can plot the force acting on the internal hole on the end of the link there. That's a representation of the force there. So the size of the arrow is related to the magnitude of the force, and its direction is the actual direction of the force. We can graph the forces as well. So you can see there's time along the bottom axis here as the motion's happening. And you can see the force tending towards the negative and then the positive and the negative and the positive as its direction changes backwards and forwards. And the link sees compression and tension. So we're going to set all this up. And basically look at how to do all that. So there's a section at the start that we can skip because we set our own assembly up for this part. Yeah, just make my screen update slightly there. So there's a little bit of setup that we want to do first. The first thing that we want to do is we want to right click on that icon there, orientation and camera views, and we want to say disable. Now I'll give you the brief sort of outline of that. As we create motion studies here to kind of describe the motion of an assembly, this exact same setup is used to create simple animations. So if you were just interested in outputting an animation of an assembly doing its thing, let's say for some promotional material or to communicate to colleagues or whatever what your assembly actually looks like when it's in motion, you would use the exact same interface here. It's just that we're going to use it to actually analyze stressors, which is another thing that it's useful for as well. And this first option allows you to set, as your animation, as it would be, progresses, it allows you to move your camera around and have keyframes along the timeline so that the camera smoothly kind of transitions from one area to the next. But in terms of what we're going to do, that's pretty useless. It just gets really annoying when the camera keeps resetting to a set position, even though you want to view something different. So that's why we've turned that off. We're not really interested in creating an animation as such. We're more interested in analyzing the forces and the stresses. So we turn that off. That's the first thing. So the system doesn't have control over where our viewpoint is at any given time. We have control over it. And then the other option that we're going to change this from animation down to motion analysis. And essentially, if you hover over these, you get a kind of reasonable description of what each one of these is. So animation is the least realistic. Motion driven by key points or motors and constrained by assembly mates. That's for creating your promotional material that you may save out as a video file. Basic motion is getting a bit more realistic, as it says there. A more realistic simulation using assembly mate springs. You can put gravity into these simulations and motors. And the bottom one is the most realistic simulation, taking into account all available types of motion, providing accurate and numerical results. So our graph that we saw, those are the numerical results that we're looking for. It's just they're being graphed. So yeah, motion analysis is what we want. So let's run through the setup steps. So the first thing that we're going to do we're going to apply a virtual motor to turn that wheel component. So that's the first setup. We want to impart some motion into our motion study. So the way that we do that is, I'll just make sure I've not pre-selected the wheel, because that kind of has an effect. So I've pressed escape, not got the wheel selected. That icon there adds a motor onto a component. And then depending on what the component is that you click on, it can be a rotary motor, or it can be a linear actuator, or an oscillating kind of motor. But we want to impart rotary motion because it's a kind of cylindrical component that we're kind of spinning around a central axis. So we'll leave it set on rotary. We should then be able to select any face on the component that we want to rotate, and it will have a good sort of stab at the center axis of that component, which it's got correct. So we're happy with that. If we want to change the direction, which for this example, it doesn't really matter, but we could just use, we kind of seen that reverse direction icon before. We kind of know what that is. And then certainly the initial sort of type of motor, or the most basic, is just that as the analysis begins at 0 seconds, the motor is already running at 100 RPM in this case. Now, again, if you run this as sort of a thought experiment rather than us actually doing it, there's a fraction of a fraction of a fraction of a second there where the simulation starts and then the motor suddenly is at 100 RPM, and you get all sorts of strange shock loads happening that maybe weren't intentional. And some of the results that you end up looking at look horrendous, and the stresses in the part are well beyond what you expect them to be. And it's because of the fact that the motor's jumped from not existing to 100 RPM, or whatever speed you set it at. It's far more realistic to set this motor to ramp up at a certain rate and have control over the rate and the time period over which that rate is accelerating over. So that's what we're going to do. Rather than constant speed, which is a very basic way of setting this up, we want to chop the time of the simulation into little segments, and we want to set what the velocity is at any given segment so that it will ramp in and possibly ramp back out again in a more controlled manner. So segments. Then we get this screen. And all we're going to do here, ignore all these graphs on the right for a minute. This is what we're interested in, this little table. We're going to, first thing we're going to do, we want to set what the speed is, or what the velocity is of this rotational motor at any given time. We don't want to set up how many degrees it's actually traveled through since the last step. So we're going to set it as velocity. So velocity in degrees per second. Then we're going to add a row, and we're going to go from 0 seconds to 0.7 seconds. We want the velocity to increase to 1500 degrees every second. And now that we've entered that, you can see the effect that it has, certainly on the velocity graph on the right-hand side there. You can see it applies a nice smooth ramp. So it begins at 0, and then it gradually kind of comes in. Don't have the motion analysis on animation, just animation and basic motion. It could be that person that's just said that do you definitely have, so who is that said that? That was Hamish. Do you have that button as an option in your SolidWorks add-ins, SolidWorks Motion? Or if it's not available there, try looking in Tools. Yes, but it's grey. Ah, right. Okay. Anybody else in the group? Uh, are other people in SolidWorks Motion, and are they following along okay? I just want to do sort of a poll of whether this is just an option on Hamish's install or whether it's across the board. Yeah, so some people have got it working. Those people that have got it working, Connor, is yours a local copy or is yours on virtual desktop? Yeah. It is available on remote desktop or virtual desktop. Right, okay. I had assumed, in fact, I thought I'd experimented. I think when you're doing the install, there is actually an option. So I'm just searching for some of my videos. Just give me a sec. I don't know, those people that are having troubles, whether it would be feasible for you to jump onto virtual desktop halfway through now. Yeah, it was kind of this bit on my video that I sent out where it was how to upgrade your SDK installation to the SEK. I'm sure I said tick the motion option as well. Yeah, it may be that you didn't tick that motion option when you did the upgrade, which is okay. You can drop back in using the same serial number. It will already be entered in there, and you should just be able to tick SolidWorks Motion using the exact same serial number. That would probably cure that. In fact, I'm 100% sure that will cure that problem. But otherwise, yeah, the remote desktop is the way to go. If you're really having issues getting the local version of it, getting this option working, the full motion studies, then use the virtual desktop version would be my advice. Yeah. If you want to try the upgrade again, what I will do is I have the other version installed on my other machine. So I'll double check that the motion section is fully featured, because as you can see in this video that I made, I ticked it as an option, but I don't think I investigated it when I booted up that version of SolidWorks. So yeah, I will double check and check that if you do tick that option, it does work for you. But you've always got that fallback position of using the virtual desktop. The virtual desktop versions do obviously work because we've got people actually on them now. So yeah, maybe watch the rest of this. There'll be a record of this, and there's already a recording of this kind of bit of the tutorial already on my YouTube videos. So you're well covered in terms of running through this at your own pace. So back to what we were doing, if I can sort of pick up my thread again. So we were setting that motor up. So let me just delete the motor and we'll come back in again as if we didn't do it in the first place. Could you quickly open the function builder page again? Not sure what values you put in. Yeah, I'm just about to drop in there. Don't worry about that. So that was part of instigating a motor in a motion analysis. So what I did, I clicked on the motor icon, clicked on the component that I wanted to add this rotary motor to, that component. It successfully identified that it was a circular face that I was clicking on, so it found the center axis, okay. And then rather than a constant speed, I want to set this as segments. So that segments the time of my simulation, which is currently set to a maximum of 5 seconds. You can see that there. That's kind of the default length of the simulation. So segments. Then I drop into this screen, and all I do is tell it at a certain time value what I want the motion to be. So currently it's set as number of degrees displaced by the component, but I want to set it as a velocity, so number of degrees per second. So change that from total number of degrees moved to velocity, degrees per second. And then I just start adding rows into this table. So click to add a row, set my time period that I want to kind of govern for this step. And for this one, I want it to stop at 0.7 of a second. So that time period's been set from the beginning of the simulation at 0 seconds to 0.7 of a second. And within that time period, I want it to eventually be at 1500 degrees per second. And then when I press enter in that cell, the graphs on the right hand side kind of give me a readout. So I can see that the velocity kind of ramps in nice and smoothly over the course of 0.7 of a second from my initial, which is 0, obviously, up to the final velocity. And then all I'm going to do, I'm just going to put one more row in. I just want to hold it at that velocity until I get to 1 second. So this time range goes from 0.7, so it picks up where that one left off. And then I have to set that I want that velocity to be maintained across that time period. So now you can see it ramps in up to 0.7 of a second, gets to its maximal velocity, and then it kind of holds that velocity there. And the reason for that is, having run these simulations a few times, you kind of have to give it a certain period of time to almost stabilize so that you can see regular kind of peaks and troughs on the stress values that we're getting. Yeah, there is sort of a tendency, if it's too near in terms of time to the point at which it was accelerating or decelerating up, that kind of corrupts the results slightly. So you kind of have to run it at a constant rotational speed for at least a period of time. And the periods of time that we're talking are quite small. And the reason that they are quite small, so I've kept everything that we're going to be looking at within a 1 second window. The reason for that is similar to the reason that we play around with the mesh size and that we try and minimize the amount of design study cases. It's just a calculation time constraint. So the longer the time period that you run this over, the longer the calculation time will take. So it's about efficiently using the computing power of your particular system. So try and focus in on the thing that you're interested in, rather than just leaving it as a vast, long, thousands of calculations style motion study. So yeah, that'll do in terms of the motor. So we can just click on OK. So we've set that up. We can click to tick on the motor. We don't want to set any other options in here. Tick. And then that rotary motor should appear in our motion analysis tree down here. So you can see it's there. Mine's called 2 because I had one initially and then I deleted it. That's all. So what I might do, you can drag this motion analysis portion of the screen upwards as well. If you need a bit more space down at the bottom of the screen, you can just click and drag if the kind of list of features here gets too big. So let's see if I can remember what order I did all these in before. So there's a step in the PDF there, which again that's kind of related to if we'd used the existing assembly, so we can kind of skip over that. We've already done that option where we switch off the orientation and camera view keyframes. Now what we want to do is reduce the overall sim time to 1 second. So as I said initially, it defaults to 5 seconds for the length of the overall simulation. And the way that you affect that is this at the top of the simulation model tree there, there's a black bar, and if you just click on the diamond at the end of it and hold, you can drag the length of the simulation back or forward to whatever you want it to be. So I'm going to drag it back to 1 second and let go, and everything gets cropped back to wherever I dragged it from. Then, because when I eventually get my readout, I want to be able to fast forward and rewind through my 1 second with a little bit more finer detail than I've got now. I'm going to zoom into that 1 second. So I'm going to make that 1 second appear across the majority of the screen. So the way you do that is just these zoom in and out icons at the bottom right there. So click on that one a few times and you can see, well, I'll go back a little bit. Yeah, that's okay. So that's more useful. Then I'm just trying to go by the PDF just so that people that end up following the PDF aren't following something significantly different. Right, I think we'll do a calculate. So the way that you let the system calculate what motion is going to occur within your assembly is, once you've set everything up and you've added any motors that you want to add, and if you've added gravity in, let's say, or any other forces, springs or dampers or contact, you then have to click on that icon there. So that kind of calculates what will occur in the motion simulation. So that icon there, I think it's supposed to look like a calculator. So we'll click on that and it runs through its 1 second. You see it spin round a few times and everything seems okay. So that's what we were checking for. Was everything running okay? It seemed to be. What can occur sometimes if the mates that you put in aren't adequate to hold anything in place, you can get components flying off into infinity or separating, let's say, but it seemed okay to me, that. So what are we going to do? I think we will generate a force plot. So when we came into this tutorial, what I said that we're ultimately looking at is the stresses that are going to be inflicted on that link as the system spins, as this powered green component spins round. What kind of compression and other forces are kind of sent through that link component there. And the first step to looking at that is to figure out, as this 1 second passes by, what are the forces acting between that pin and the internal bore of that link component. So when I say the internal bore, I mean that face there. So that face there is in contact with that pin, and where they contact each other, there's a reaction force. As the link forces the bearing block to go backwards and forwards, the bearing block is resisting that movement. So there's a force between those two. So I'm going to graph that force now. So if I can drop back into there, it's just temporarily kicked me out of the motion study there. So I want to graph it. So I click on the little icon that looks like a graph that's got an X and Y on it. So results and plots. There's a lot of options in here, but I've kind of already said we're interested in forces. So we're going to select forces from the first one. I've already said that it's a reaction force between a component pushing on another component or pulling on it. So reaction force. Again, you can see all the multiple options in here. There's a lot of submenus here, depending on what you're looking to graph. And then, because of where we're headed with this, what I'd like to do is I'd like to resolve these forces in terms of their X and Y components. But that begs the question, is that X and Y in terms of the overall assembly? Because there's an X and Y in terms of this assembly, but there's also an X and Y direction that's stored within that link as well. And I would say it's the one within the link that's the most useful, because we're ultimately going to be talking about what stresses are acting within the link itself. So it would be good to have those kind of force figures related back to the X and Y in terms of the link itself. But before we do that, we're going to enter something in this box here, and if we hover over it, it will tell us what it's looking for. Select one mate or simulation element. So the mate element that we're going to select is the concentric assembly mate that we put between that cylindrical face and the internal cylindrical face on the link. That is the assembly element. And then the other thing, and or one face of a part attached to it to create the result. So we're going to select that face, and then we're going to select the face that is inside the link. And the way that you've got to do that, because you can't click on it here because it's been obscured by that pin that's passing through, you have to place your pointer where you think it is, and then right click, and then go down to select other, and then you get a list of things underneath your pointer, and you sort of hover over each one and you try and ascertain which one it is that's that internal cylindrical face, and I believe it's that one. Oh, sorry, I skipped a step there. Yeah, I went in the wrong order there. Sorry about that. So this one, we're going to select the peg that sticks up out of the bearing block, and we're going to select the concentric mate. So there's a concentric mate between the bearing block and the link, and in order to find where that mate is, I can't click on it in the graphics window because the mates aren't visible. They're invisible, but I know they're there, and what I have to do is browse inside the assembly itself. So if I click on that arrow there, you can see the assembly is all available to me as if I was in the feature manager. It displays it over the top of the graphics window. So then I want to browse inside the bearing block, and then there's a folder in there called mates. So the concentric that I'm interested in is in there. So the concentric mate is what's tying that bearing block to this link. The face that's going to be half of this reaction force is the face that I've selected there. And then the component to define the X, Y, and Z direction, I kind of said in the wrong order, but I want it to be the link. And when I click on it, the X, Y, and Z relative to the link get displayed. So the reason I've chosen that is because as this link moves backwards and forwards, its relationship to the assembly X, Y, and Z directions changes because it kind of swings backwards and forwards as it spins round at one end. So that would be kind of nonsensical. Wouldn't really be of any use to me. But if I can resolve these forces into X, Y, and Z relative to the link itself, that is more useful to me. So if I get a force in X, I can use that figure to set up my own simulation just using the link itself and just apply a force in X to try and crush the link. So that would be more useful. And the same in Y as well, and arguably Z, although Z is going to be minimal. So is there anything else? Aha, yes. This option here. So what we can do is we can resolve these forces into X, Y, and Z, which is what we are going to do, or we can just have their magnitude, which is just a figure, and we will never know what direction that is acting in. So as I've already said, what we're going to do is we're going to resolve them into X, Y, and Z components, which is far more useful to us. So I think the first one that I'm going to do is the X, which I suspect is probably the largest of the three components. So X. And then if we click on OK, I then get this little readout, which is to translate what SolidWorks is saying to me. It's basically saying you are using the assembly mates to artificially link these components together. Would you like me to more realistically link them together using virtual bushings between each one. So virtual kind of plane bearing surfaces between each one that will give you a force readout as to how much each bushing is pushing against the peg or the bore that it's actually in contact with. So the answer to that is yes. We would like that. And then we get our readout. So let's play around with our simulation and see if we can understand a little bit about what's going on here. See if we can try and reason out what we're actually seeing. So what I want is, I want to be able to see the assembly itself. I want to be able to see the plot of the reaction force between the peg and the bore that it's sat in the link arm there. And then if you click and drag on this line on the timeline, you can drag to the points that we're interested in. And beautifully there's a point which is seeing quite a large force. So the negative and positive here on the reaction force. Did we set it to reaction force or reaction moment? I'll go back in and check in a second. But, so yeah, it's where the bearing block changes direction. So it's slid all the way to one end of the slot. And you can see the wheel is essentially, if we look at it from that angle, it's essentially at horizontal. It's just gone past. But basically, this bearing block wants to keep accelerating to the left, but the wheel isn't going to let it. It's slowing it down, so it's working against the momentum of the bearing block itself. And it's trying to change its direction to go back in the other direction, which is why we're seeing a spike in the reaction between the two. And then if we run it a bit further, we should get a similar situation at the other end. Yeah, it's over at the other end now, so it's other limit. And again, it's about to change its direction. So it was traveling, let's say, left to right, and it's now being forcibly slowed down, and its motion's been reversed. So again, we get a spike in the reaction force between the two of the items that we've selected. So that's quite useful. There's a few things other than that we can do, and that is that the sort of jumps in this graph, I'm not terribly happy with them. I'd like a sort of, this is at 25 frames a second, which is the default. I think what I'd like to do is have a little bit more detail in these graphs and have the sample rate a little bit higher. So I think what I'd like to run this simulation at is about 100 frames a second. And then these graphs will be kind of more detailed. They're a bit sawtooth at the moment. So you can do that as well if you go into motion study properties, which is that cog looking icon there. 25 frames a second motion analysis. Bump that up to 100. Now, obviously, because we've increased it to 4 times its previous sampling rate, it will take 4 times as long to calculate this simulation because there's 4 times as many frames. But it's still going to be a pretty quick sort of calculation time. So I'm going to click on calculate, and it's going to run through again. And then, yeah, there you go. There's a really concerning spike there, which I don't like the look of, which is probably warrants further investigation. But that is a more detailed graph. Oh, that's interesting. Yes. Anyway, we'll not get too hung up on that. I think we've just gone over time as well. Save what you've got there. Save what you've got. We'll drop back into it. We'll conclude that because there's some stress analysis that we want to put in. I've just noticed that mine has got a bit of interference there as well. I don't like that. I might sort that out for next time. Yeah, there's something strange happening there. But yeah, press save on yours. We'll drop back into that next week. We'll complete that little bit, and then we'll move on to static assembly stress analysis as well, which is kind of a different part. And we will refer back to that kind of flow chart because it's kind of important that we get those kind of three basic styles of simulation kind of embedded in our heads. We can run a fully static simulation on an individual part. We can run a fully static simulation on a whole assembly, or we can run a motion analysis with a little bit of stress analysis sort of sprinkled in there. Yeah. So as I say, save it, and we'll drop back into that, and we'll continue it next week. And the people that are having issues getting the motion analysis working, yeah, don't spend too long trying to reinstall it. I don't mind you spending a bit of time, but it may be a bit of a lost cause. If you want to drop into the virtual desktop, that might be better. Okay, I think I'll sign off. I'll see everyone next week.